students, welcome to next class, that is class 12. Okay, so in the previous video, so I said you that we are going to complete the unit 1. Okay, this is a finishing brushing part I am going to do with unit 1, and we will start unit 2 today. So in the previous video we had seen the molecular orbital diagram of the arene. Okay, and I have told you the different orbitals, how they are going to bind with the different metal orbitals, is it right? And how many group Mulliken symbol we can show for this one, psi1. So I said you psi1, it is A2U. Okay, then psi2, psi3. So what I said, it will have the because of center of symmetry, so will have the E1G. Okay, psi3, psi4, psi5. So again here, so no symmetry, so ungrade, so E2U. Okay, I have told you, so E2U, this will be there. And for psi6, so that is B1G. Okay, so B2G, so B2G. So these are the different molecular orbitals of the ligand we have studied in the previous slides. Okay, so A2U, E1G, E2U, and B2G. Totally how much? So you can see 1, 2, 3, 4, 5, and 6. Okay, so this is of 6 carbon, so 6 molecular orbitals is going to generate. Now if you want to go for the MOT, if in the examination if they ask you draw the MOT of dichromium benzene or something like that. Okay, so anything, so like in ferrocene, if they ask so I had given you one diagram here, so like this. Okay, so in yesterday's class I had given you the diagram how of ferrocene we had put here. So similarly for benzene, what we have to do now here, so instead of cyclopentadienyl, so you have to go for what here, so 6, so like this. So 2 this you have to take, so instead of this one you have to take 2 benzene here. Okay, 2 means how much orbital will come here, so here it is 10. If cyclopentadienyl is there, it will come 10 molecular orbitals. We have shown here like this. Okay, 10 orbitals we have shown it here. Similarly, if it is arenes, we have to show how many, 12 now. 6 carbon of this, 6 of this, so 6 plus 6, 12 molecular or atomic orbitals we have to show it here. So how it is, so I have here we have taken it here for the benzene. I have shown you that is A1G, A1U, same it will come. And for next one's E1G, E1U, next E2G, E2U. So up to here it is same. One more you have to add here, that is your B1G, B2G, like this. Okay, this is extra for your arene complex. So how much it becomes now? See, if it becomes now, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, so it has come of this 12 molecular orbitals. Okay, so this is how you have to generate only one here. In the ferrocene you have up to here, so in benzene you have to generate this one here, and this remains the same. Okay, 4s, 4p, and 3d, 4s, 4p. Okay, so 4p, p means A2U, this one A1G for S, and D for same. So this remains the same. Only thing is you have to add one more here, and rest of them become same now. So this will be here, and whatever you are generating now here, everything you generate anti-bonding also, and just to touch all the things like this wherever the symmetry is there, so you have to touch it like this. Only part becomes what, this important part will be the important part here. Now you can generate the magnetic property similar to the ferrocene for this diamond also. So like this MOT, so this you do in the home and practice it. Okay, and don't bother about all these things. This is very much important for both things, and the symmetry Mulliken symbol here, and just to manage it. Okay, so here's all whatever the bonding we are adding here, so same anti-bonding states here, and remaining E2Gs here like this, E2U, like this you have to go and doing. Okay, small things you can show here like this, and main concentrate on this here and filling of the electron. So this is what about the geometry of this yesterday's class. Okay, and this is what about MOT of arene molecules. Okay, so cyclopentadiene, arenes, everything. So one more thing to be I will want to conclude here, that I think I have shown for cyclo this one, what is that, cyclo allyl compound. Okay, so I think I had given you the allyl compound, so like this. Okay, 1, 2, 3. Okay, so for allyl compound, what is this here? So this is plus, this is, take it like this, plus, and this is plus, like this. Okay, so I have given you molecular orbital for the allyl compound here. So if the metallic orbital, how to coincide here or overlap here, so that we did not, I think I did not discuss. It's very simple. The pentadienyl and arene complex I have said you. Similarly, you take the axis here also. If I take this axis here, x and y and z here, so you have to generate now. So now for this, what I said you, so best orbital will be 4s, is it right? So this is a confirmed for the psi 1, so you can take it as a 4s here. Okay, so 4s orbital can overlap very nicely for all this psi 1. Next is what, z orbital, that is a confirmed here. So this is z orbital, so you take the z orbital and fix it here, and you can overlap it. Okay, or you can take this like this and you can overlap in this way, like this. You can overlap. Okay, so here it will like this. So this is what about this z orbital. So 4p z orbital, and one more we can go, that is your 3d z square orbital. Okay, so this also we can go 3d z square orbital, like this. Okay, so like this. So this also I can lift it here and I can fix it here somewhere, like this. Okay, so like this, the three orbitals are very good in the bonding here for the psi 1 allyl compound. Okay, so 3, like this. So similarly for psi 2, I said you, so what is that? So you take here to one node, you can generate here. So when one node is generated here, so this becomes plus, and here it becomes plus. Now you see here, so this is one node is there. Now this is not going to bind here. So best which will go now here to bind here, that is your 4px. So this px and 3dxz, 3dxz, somewhat see 4px. So now 4px, how we can draw it here? So this way I can draw it here. So like this. So you have to see here x here. So similarly, so you have to draw here. So you can turn it like this. Okay, now you can join it like so. You remove this orbital here and you can fix it here like this. See, like this. You can fix this orbital here. So this will overlap here, and this empty will minus will overlap here, like this, plus plus. So this is how we can overlap for this 4px. Similarly 3dx, 3d what is the xz here, 3dxz. So you see here x is here and z is here. So I can draw in this way, like this, like this. Okay, so like this I can draw like this, 3D xz. So now I can lift this and I can fit here. See, this is shaded, so shaded here. So I will draw here and I will fit here. See, like this and like this. So this is shaded to shaded, minus to minus here, like this, like this, like. So it will fit here and it will overlap here nicely. So like this, 4px and 3dxz can fit over to this. Next one is what? Last one, that is your what is that, 3 nodes, that is here and here. So one node and two nodes. So you generate again here overlapping like this. Okay, now node means what? Here if you take positive, here you take positive, and here you take positive, like this. Now 3 generation of nodes will be there. Now see, 2 nodes means out of plane. Okay, so that is the binding is very difficult here, out of plane. Now you have to see here. So y will come into consideration here. Why? Because this is out of plane. Okay, so this will come into here in this, because of the 2 node here. The orbitals are placed very arbitrarily here, not in the proper plane. So same thing while overlapping also, this also goes out of plane now. So y will come into picture here. So what will come here now in last one, 4py. So 4py somewhat tilted like this, something like that. Okay, this way out of plane you are going to get, this is going to overlap here, 4py and 3dyz again. Okay, so this also something something out of plane like this. Okay, so 3dyz. So like this 3dyz and 4py. So these are the orbitals which can overlap lastly for this. Okay, which is out of plane only, y orbitals, like this. So these are the combination, but this is very poor overlapping. And finally, which is left now? So 3d x square minus y square is left, and 3d xy, 3d xy is left. These two orbitals are left now. Okay, 3d xy and 3d x square minus y square. Yz we are xz we are used here. So these two are left. So what happens for these two orbitals of metal? They remain non-bonding. They remain non-bonding, like this. Okay, so this is how you can show for every molecular orbital diagram the overlapping criteria of the metal versus molecular orbital of the ligand, pi orbital of the ligand. So like this you have to generate. Okay, so this is how I have told. So only this I had told you in the previous video 2 or 3, I think. So this much I had told you of allyl compound. ligand here, radical, but here I have shown you the metals how they are going to overlap with this also. Okay, so this is how even cyclopentadiene also now is we have completed. Arenes also we have done very good matching, okay, with MOT diagram of ferrocene, MOT diagram of dibenzene chromium, and all others. Alene also no problem. Alkyne also is okay now, which depends on your which Duncan chant model here. Okay, and followed by cyclobutadiene also we have done it here. Okay, cyclobutadiene, butadiene, 1,3-butadiene also we have shown like this. So that's what this is the important part we have completed in the unit 1. So you have to draw very nice molecular orbital diagram and represent in the notes properly. Okay, this is what you have to keep in the mind. Now if we go for some of the notes, okay, note before ending up this unit 1. Now if I ask you whether it is possible to undergo the Friedel-Crafts reaction for the metal arenes, okay, like this. Friedel-Crafts reaction means what? In the presence of CH3COs, acetyl chloride, and AlCl3. Like in ferrocene, whether it is possible? It is not possible. Okay, so this you have to keep in the mind. They will ask why it is not possible. Because benzene here, what happens here? It loses now electron because of the metal here. So metal gets a little bit negative charge, and benzene will lose and it have some partial positive charge. And being electrophile in this Friedel-Crafts reaction, it will not attack for the positive charge unless you use some drastic condition. Okay, so this is not possible. So this has been proved by spectroscopy also. So carbon NMR spectroscopy, as I told in previous video. So what will happen in this spectroscopy, it states that the arene molecules is highly shielded. So what does this states? In the previous slide I have shown you. So this is states that the this is highly shielded. So benzene is highly shielded, okay, by the nearby metal here, by the nearby metals ions here. So that is why so that is why, because metal is there, metal also has the electrons here, and that's why this whole thing is very shielded here. So that is what you can see through carbon NMR, and that's why this arene complexes, that is metallocenes, is not going to show Friedel-Crafts reaction. This thing you have to keep in the mind. One more thing you have to keep is what, if we are having like this different benzene rings, okay, something like that, different benzene rings like this in a molecule, and if metal is there here, so with whom it is going to bind? Some questions they may ask like this also. So to keep always in mind that among all the benzene which is highly aromatic in nature, so metal is going to bind to that ring here. So after rest is you have to keep it this one. So highly among different benzenes which is highly aromatic in nature, so metal is going to bind for that. This one note you have to keep in the mind. Now note number 3, if for example in some cases they ask like the CPM, okay, that is cyclopentyl metal nita6c6h6. So this compound they will give nita6c6h. Now they will ask find out what is M. Now see what is M means what? Metal. They will not, they will has not given, but they will ask you to find. Now what you have to do here, cyclopentadiene, you know, number of electron donation by CP is 5. Okay, now nita6 he has given already, so number of C6 has donated is 6 electrons. So total how many? 11 electrons happens here. Okay, now how much required for 18 electron? So I think 7 is required. Okay, so 7 means it becomes 18. 7 means what? That is your manganese. Okay, so that is your 3d5 4s2 5 6 and 5 6 and manganese. So M is nothing but your Mn, like this. So this is way, this way also there are some questions asked in the competitive examinations or in regular examination also. Okay, so now here up to mark we have completed our unit 1. Unit 1 is completed. Okay, now we will go for today unit 2. See, okay, so prepare yourself. I said you in the mail also, WhatsApp also, that be alert. So we are very heading up to the completion of the unit 1. Okay, so now we are starting the unit 2 also, and by the 12 to 15 12 slides I'm going to complete this also. Okay, so be very alert for this all the concepts. Okay, if you don't understand, you can make all the points and bring in the Zoom meeting so that we can discuss that. Okay, so first this we are going to is fluxional behavior. Okay, in unit 2 he has started with fluxional behavior. What is fluxional behavior in organic compound? So this fluxional behavior I showed you is dynamic equilibrium interchange. Remember this. Okay, in one case I have told you it's a dynamic equilibrium interchange between some or all atoms in organometallic complex or compound, in organometallic complex or compound. See, okay, so this is what about the fluxional behavior. So this happens when the molecule is non-rigid. The molecule should be non-rigid. So in this case only we can see the fluxional behavior, like tautomerism. In tautomerism, was enol and ketol form. Enol and keto form we are going to see in tautomerism. Is it right? So this is also one type of interchange of the atoms here. So enol forms and keto. Keto means oxygen. Enol means OH group will be there. You see, just check it. Okay, in organic compound. So that is, we call it as a tautomerism. So this is type of the behavior. So but this also happens to be non-rigid type of molecule, and this happen but it can be separated. Okay, so we can know that, and we can specifically separate it here. Similarly in isomerism, so isomerism also we have taken some cis trans, so other things we are going to get here. But problem is we can separate in this also. Okay, in different compounds are getting, and we can separate in this also. Okay, like this resonance also. If you say resonance, what happens? Resonance, there is interchange of the electrons. Electron jumps from one another. Haeckel's rule, you see benzene, three resonance structure we can show where the bonds. So that is the electron change, not the atoms. So atoms will not jump from one to. So this is a resonance. We call it as a resonance, like this. Okay, so in this way, in this concept only, this fluxional will come. Fluxional means what? Definitely they are also non-rigid, but you cannot separate here. That is important. You cannot separate. Absolutely. Whatever the first compound you have started, okay, whatever the first compound you have started will end up with the last compound, and you cannot identify only. So that we call it as a fluxional fluxional behaviors. Okay, so this thing you can keep in the mind. Okay, so they are having the molecules are equivalent in terms of structure. So here in fluxional, so molecules are equivalent in terms of you can say structure, then in terms of bonding. Okay, and in terms of energy. It's like this. So if you see, they are same. So fluxional behavior means what? In equivalent this is having the molecules are equivalent. Okay, they are having the equivalent in terms of structure, in bonding and energy. But in other, what I said now in previously, tautomerism, isomerism, resonance, this, that, so there may not be the same here. So here it is almost the same here. So that type of property we call it as a fluxional behavior. So best example to start with this fluxional behavior, usually we go up with the PF5, okay, phosphorus pentachloride, so which is a trigonal pyramid like this. Okay, so here F like this. Okay, so TBP, we can show that this is having the TBP type of structure. Okay, so this is your TBP structure, and we can donate it from fluorine 19 NMR studies. Okay, so from fluorine 19, if you see the NMR study at room temperature, if you see, okay, so it is going to show you only one signal. It is going to show you one signal, but somewhat it is having some doublet type of like this. Okay, one signal, but some doublet will be there because of the axial and equatorial. These are the equatorial fluorine, and this is a axial fluorine. Okay, so this is a axial fluorine, and these two are the equatorial fluorine. Okay, and we can see that at the room temperature you are going to see one signal because of what? One signal only, but some small doublet will be there because of these two fluorines, but single only you are going to see in the fluorine NMR here. Okay, next what will happen now? This get interchanged now. So somewhat this will interchange into one. Okay, so like this in a square planar now. So F like this. That is your SP, square planar structure. It is going to interchange in this way, square pyramid. Okay, structure is going to interchange in this way. And finally you can see that if I in order to mention the fluxional behavior, I will mention it here. So yeah, I will take it as here F1, here F2. Okay, then I will take it here, this one as a F3, this one F4, F5. Okay, F1, F2, F3, okay, F4, F5. So we do know this change, how it happens. Now what will happen now here? So when I take it here, so see here, now finally what I am going to get here after this square pyramid type of intermediate, same thing I will get now here. So like this, I will yeah, so like this, like this. Now I am going to end up with this same structure now here. But see here what happens here, F4, F5 will come here, F3 remains same here, okay, and here F1 and F2. So like this. So I am going to get in this way. See here. So initially how it was here, it was F4 F5, F4 F5 has come here now. See here. So which was axial, F4 F5, now it has come to where, F4 F5 equatorial. See here, it has come to equatorial, and F1 F2 which was equatorial has come to F1 F2 axis. See, so very, but here what happens now, again here TBP is here, this also TBP, this also TBP. Interchange is here, where you can see here this F1 F2 whatever, this will be shifting now here in intermediate, and they are having the change in the geometry also. Okay, these bonds will shift now here, somewhat changes will be there, okay, like this. And finally you are going to get here like this structure where the atoms are totally changed from axial to equatorial and equatorial to axial without knowing. And what happens, you know, and here at low temperature, at low temperature, that is around minus 100 degrees centigrade, okay, or 110 degrees centigrade, 110 degrees centigrade. So what you are going to observe, same thing if you take the fluorine 19 NMR here. So you are going to get the two signals. See, this is very much important. You are going to get two signal. So here particularly two signal you are going to get. So you are going to get two signal, not like here in one signal. So here particularly two signal you are going to get for two different fluorines, that is your axial and equatorial, for axial and equatorial. See, is it right? So this is what we can we can say that fluxional behavior. See here, it is only one it is showing, is it? That means there is very fast movement of the fluorine. You cannot be distinguished by the spectrometer also, so that much fast. So one peak you are getting, but as you decrease the temperature, what will happen now, it is the meter is so this one, because it becomes rigid, okay, as I decrease the temperature, and the movement of the fluorine can be noted by the spectrometer, and that's why you are going to get the two peaks here like this. Okay, so this is how we can, and this interchange can be shown by Barry's pseudo rotation. Okay, pseudo rotation, Barry's pseudo rotation method. So what is, they will ask sometimes, Barry's pseudo rotation. So very simple it is. So you start with, I will take it here again here, we will go with the P here, okay, and or you take any metal here, M, okay, and we'll go for like this, okay, same trigonal pyramidal, this only will go it here, okay, so like this, and we will take it here as a axial. This is your axial and this is your equatorial, like this. Okay, so this is what happens in the pseudo Barry's pseudo rotation. Okay, Barry's pseudo rotation technique. What will happen now? So in the next moment you can see here, so these two will come like this, rotate in this way, and this A is going to come in this way, like this. So A will come like this and E is going to come in this way, and you are going to get the square pyramid type of structure, that is somewhat like this. So your metal is here, somewhat you can show here like this, so this is where axial is coming down, and similarly equatorial is also coming to up here. So this is equatorial, this is equatorial here. Now equatorial is going up to the axial and axial is coming down here, and finally you are going to get your that compound, that is your metal, and you can see here. So like this, and here like this, that is your whatever axial was there, whatever equatorial was there, it will come to equatorial, and axial come to here, like this. Again you are going to get the TBP, again you are going to get the TBP. See here. Okay, so this type of square pyramid and TBP. So which was equatorial will come to axial, and which was axial will come to equatorial, axial will come to equatorial, like this. Okay, so this type of rotation we call it as Barry's pseudo rotation. Okay, so whereas this remains constant, this remains stagnant, only these are going to have the rotation, that is axial and equatorial. That rotation we are going to, that exchange in the atoms we are going to observe. Okay, so that type of this we call it as a Barry's pseudo rotation. So this is how in today's video we have learned the first concept of unit 2, that is your fluxional behavior. Okay, in the next video we will learn little bit more examples of this fluxional behavior along with the second concept of unit 2, that is oxidative reductive of the or heterogeneous homogeneous catalysis in the organometallic chemistry. Okay, thank you.